Nvidia controls roughly 90% of the AI chip market. Governments are literally stockpiling their hardware as a matter of national security. So when an underdog startup built a new piece of silicon that ran top-tier language models up to 10 times faster than Nvidia's flagship H100, Nvidia didn't just try to out-engineer them. Instead, they paid $20 billion to license the technology. And I'm not even joking. So what exactly did this startup Groq actually build that terrified the 900-pound gorilla of the semiconductor industry? And if this tech is truly that much faster, why hasn't it replaced your GPU? This is an LPU, a language processing unit. To understand why this chip is such a massive threat, you have to understand a fundamental lie we've all accepted about AI hardware. A GPU was never built for AI, it was built for gaming. It was designed to render millions of pixels at the exact same time, in parallel. And to feed that massive parallel engine, modern GPUs rely on HBM, high bandwidth memory. HBM is amazing at holding massive amounts of data, like an entire 70 billion parameter language model. But generative AI, specifically the part where the AI actually talks back to you, called inference, is not parallel. It is sequential. It is an autoregressive process. That's a fancy way of saying the AI has to guess the next word, and then use that new word to guess the next word. It cannot generate word 5 until it finishes word 4, which means every single time the GPU generates one word, the compute cores have to reach out across the chip, grab the entire multi-gigabyte model from the HBM, bring it to the core, calculate the word, and then throw the data back. It does this for every single token. In computer science, accessing external memory is like walking across the city to fetch a single piece of paper, reading one sentence, and walking back. Doing this hundreds of times a second creates latency. That's why a standard Nvidia H100 cluster running a model like Llama 370B maxes out around 30 to 40 tokens per second. Groq looked at this and asked a very dangerous question. What if the model never had to leave the chip at all? What if the data had no commute? Their solution was the LPU. It doesn't render graphics. It doesn't train models from scratch. It doesn't even use HBM. Groq ripped out the external memory and replaced it with SRAM, static random access memory, baked directly into the processing die itself. The compute cores and the memory are physically touching. The internal bandwidth hits a staggering 80 terabytes per second. The data is instantly available the exact millisecond the core asks for it. But they didn't stop there. Because the LPU only runs language models, they realized they didn't need 90% of the complex logic that makes a GPU versatile. They deleted the hardware schedulers. They deleted the branch predictors. Simple. They deleted the rest of the chip. They turned the silicon into a dumb, perfectly timed assembly line. A software compiler maps out the exact route every piece of data will take before the model even runs. It is entirely deterministic execution. The result? Where an Nvidia GPU takes 200 to 400 milliseconds to give you the first token, Groq spits it out in 18 milliseconds. And for Llama 370B, it pushes nearly 400 tokens per second. It's so fast you can't even read the words as they appear. But here's the catch. When every bit of memory needs 6 transistors to hold it, which is what SRAM requires, your memory footprint explodes in physical size. You simply cannot fit that much on a single wafer. Which means a single Groq LPU only holds 230 megabytes of memory. Now, you might be thinking, wait, a 70 billion parameter model takes up roughly 140 gigabytes. How do you fit a 140 gigabyte model onto a 230 megabyte chip? You don't. If you want to run a large model on Groq, you have to split it across hundreds of LPUs. That sounds like a death sentence for latency until you see what happens when you stack them. Because the architecture is entirely deterministic, Groq's compiler forces 256 independent chips to act as one flawlessly synchronized brain. They pass the model fragments down the assembly line over their real-scale interconnect without a single clock cycle wasted on scheduling. But there is a brutal, honest limitation here, and it's exactly why GPUs aren't dead yet. The LPU is an undisputed monster for a single user asking a question in real time. But if you are a massive cloud provider, and you have 10,000 users asking questions at the exact same millisecond, the LPU hits a wall. It lacks the massive memory capacity needed for high-volume batch processing. If you try to run thousands of simultaneous requests, that tiny SRAM capacity overflows. In a heavy batching, high concurrency data center, the massive memory pools of an Nvidia GPU still win, period. Which brings us back to the original question. If the LPU is this fast, why hasn't it destroyed Nvidia? Because Nvidia realized the future of AI isn't just massive batch processing. It's real-time, low-latency voice agents and robotic control that need speed-of-light responses. Nvidia saw that Groq had solved the sequential inference crisis. So in December 2025, they dropped $20 billion to license Groq's IP. They didn't just bury a competitor, they bought their own future, embedding Groq's deterministic architecture into their upcoming hardware roadmaps, while Groq took the cash and transitioned into a highly specialized AI inference cloud provider. The inference crisis is being solved. But the real threat to AI isn't the chips at all. It's the 140 kilowatt server racks that are literally melting down data centers.